Well, welcome everybody. We're back, and we're back for our very last webinar, unfortunately, in the current series. It's gone very quickly, I feel. Maybe 2020 has kind of dragged on a little, but we're getting near to Christmas now, so we're going to wrap up our webinar series. But I'm sure that we'll be back in the new year with a new series of new and fun things. If you'd like to collaborate with us, we'd love to hear from you. So let us know if you'd like to do that. This webinar, we are joined for a transatlantic experience. So we've got Andrea Zani from our San Francisco office. He's a senior facade engineer. And then we've got Carmelo Galante from our London office, and he's an associate facade engineer. And they're going to be talking about the facade and environmental design 8,000 kilometers apart. So the differences between the US and the UK approaches, and looking at some case studies. And I've seen it before, and it's sounding very good, guys. So I'm looking forward to it.
Thank you.
A very quick kind of thing: if you're not familiar with the LiveSwarm software, then just a couple of things. We've got a chat function. So if you can just see over on the corner of your screen over here, so the chat function. So let us know, say hello. Wish us all a happy Christmas. We wish you all a happy Christmas. So you can put all of your little chats in there. There's a questions tab. So if you would like to ask any questions, then we'll ask those at the end. But you can rate the questions. So if you see one that you like, give it a little thumbs up, and that'll mount it all the way up to the top. And then, so all that is left for us to say is that if you have missed any of the webinars in our series so far, I'll put the web address up in the little chat function, and you'll be able to watch them all back on our website. That's for both this series and the summer series. Lots of exciting content in there. So I'll hand over now to both Andrea and Carmelo, and I'll pop up later on. See you later on, guys.
See you later.
See ya.
Thank you, Catherine, for introducing us, and thank you all, guys, for joining us today. So let's get into it. Facade and environmental design 8,000 kilometers apart. So just a bit of a brief intro. So Andrea and I know each other since a while, and since before he joined UC, and I was really happy to hear a couple of years ago that he was going to join our San Francisco office, and we been collaborating quite a lot on day-to-day work, but also especially R&D work, and it's been taking a while to get used to the time difference between us. So usually when I call Andrea in the morning, he's having his first cappuccino, while it's almost a bit o'clock in the UK, right, Andrea?
Yeah, I have to admit, I'm taking most of our calls in pajamas, but it's always nice working with you and all our London colleagues on these interesting topics. So it's so cool.
I enjoy that. And we're going to talk about buildings, facades, but let's zoom out for a moment. Let's start from the bigger picture. We probably all know that what we're currently doing to our planet is bringing the external temperature to increase, but probably less of you know what are the possible scenarios depending on how we behave. And if you want to go more in depth into the topic of climate change, please look back at the webinar from last week from Max, who's been discussing a lot about the topic of climate change. Just going to scratch the surface to introduce our topic. And so if we consider this graph, the gray area is showing what is the baseline scenario. So that's the scenario if we don't apply any policies or actions again to limit climate change. And we can see that the external temperature in that case is expected to increase between 4 and 5 degrees compared to pre-industrial level. However, a few years back, the Paris Agreement was signed under the United Nations framework, and quite a few countries agreed to it, and they agreed to commit to do everything they could to reduce the greenhouse gas emissions in the atmosphere to stay within an external increase in temperature of 2 degrees and actually possible below 1.5 degrees, which is considered to be, let's say, acceptable in this sense. However, there is a gap between what we promised and what we're doing, as current policies and pledges are bringing us to an expected increase by the end of the century between 2.5 and 2 degrees in the external temperature. Now, that's the kind of global picture. Then each country is behaving in a different way and is doing different efforts. So if we consider the two countries we're focusing on today, which are UK and the US, we will notice that there's a difference between them. So the effort done by the UK, which is in line with the EU in this moment, is considered to these efforts are considered to be insufficient. Insufficient because with the current policies and pledges, the external temperature is expected to increase by just below 3 degrees. If you look at the US instead, the efforts done at the moment by the country are considered to be critically insufficient, which means increasing external temperature considering the policies in place above 4 degrees. I'm not sure, Andrea, if you would like to see something about this.
Yeah, unfortunately, given that we were not part of the Paris Agreement in the 4 years, we're a little bit behind, but let's see if in the next 5 to 10 years we will catch up at least to get aligned with the EU and UK.
Yeah, and if we look at the graph of how the external CO2 emissions have been going in the last years, you can see a constant drop in the UK with the CO2 emissions reducing constantly in the last 30 years. And we can also see in this graph on the top the effect that the current pandemic has been having with reduction in CO2 emissions compared to the last year in the range of 15–17%. We can also, it's also interesting to see how the reduction in CO2 emissions in the UK is connected to a massive decrease in the use of coal to produce electricity, which is the graph on the lower area. Well, I think in the US the situation is quite different, though.
Yeah, you're right, Carmelo. If we look at the graph on the top right, you can see that we are decreasing CO2 emission the last 10 years, but the drop is less significant compared to the UK. And also in terms of electricity produced by coal, you can see that, yes, there has been a drop, but not as consistent and significant as in the UK, and it's been partially replaced by gas, that it's just cleaner, but it's not a renewable sources like wind and solar. So if we look at the picture 10 years ago and now, we can see that we have an increase of renewable sources, solar and wind, in the East Coast and West Coast, but still the Midwest and the center of the United States are still running with coal and gas. So we have a lot of work to do to improve our carbon footprint. And what's the picture in the UK?
Well, I think the graph on the left is showing how the decrease in CO2 emissions was possible in the last 10 years. So despite an increase in that due to increase in population and GDP, the switch to cleaner fuels such as renewables, but also the increase in the energy efficiency has caused in the end like a more than an offset, and so a drop of about 29% in CO2 emissions compared to 10 years ago. And given that we're going to talk about design and facades and buildings, it's important to consider the climate in the countries we are considering. If we look at the UK and this graph, you will notice that by looking at the average minimum temperatures in each zone, that the climate is quite uniform, let's say, across the country, with colder spots in Scotland. However, it's quite different compared to the US, which is a massive country. Right, Andrea?
Yeah, exactly. Of course, the dimension play an important role. We have up to 7 major climate zones, from hot and humid to dry and cold. But for example, we will see later, just looking at the California context, that the extension is similar to the UK. You can see that we have much more variation in climate. So we definitely have to pay attention and design our envelopes based on the different climates that we have across the US. And here we just want to summarize a little bit the big difference between the climates in the US and in the UK. So we took 2 main cities for each country, and you can see that Edinburgh and London are pretty similar with the low radiation and not really high peak in temperature during the summer. Instead, in New York and Los Angeles, we have quite higher radiation, up to 800–900 watts per meter square, and the temperature in New York, for example, you have big swing compared to winter and summer, with really high temperature in summer, and instead LA is a little bit more Mediterranean climate with mild temperature. And if we step in and we look just at the built environment, we can see that both UK and the US we have buildings that play an important role in CO2 emissions. And if we look only at the major cities in both countries, we can see that commercial residential buildings play a huge role in CO2 emission, with up to 80% for both countries. So it's crucial that we address CO2 emission produced by buildings if we want to get to the targets set by the Paris Agreement. And if we looked even further in, and we take a typical New York office, for example, we can see that up to 55% of the energy demand and CO2 emission are related to space heating and cooling that are strictly related to the envelope performance. And if we instead go on the opposite side of the United States and we look at a typical California office, we see that we have 40% of cooling and ventilation related emission, of course, because of the different climate. But we still have 70% of space heating. That it's quite a big chunk of the graph. So this gives us information about how purely the envelope we're performing in California up to 10 years ago. So we have a lot of work to do, and we can improve a lot the overall performance of our building across the US, but especially here in California. How is the picture in the UK? It's slightly different, right, Carmelo?
Yeah. So the pie chart here on the left is showing the well, on average for a typical office in London, where you see like still over 40% energy consumption between space heating and cooling, with also good chunk due to lighting, which can be improved with more efficient lighting solutions such as LED. So lots of work to do. And if we go one step further and zoom in more and look at the facade. Yeah, so perhaps this diagram here is kind of showing how complex our day-to-day job, having to deal lots of phenomena. And of course, when we talk about environmental design, we need to consider how we address the solar gain, how to work with weather tightness, how to improve it, how to detail thermal bridges, or how to minimize thermal bridges, or what's the facade zone. But there are also some considerations to do which relate to environmental design, which may not be so obvious. And I think especially in California, Andrea, this is applicable, right?
Yeah, we have, I think, a perfect example that summarizes our work. Like if you, for example, in California, we have a lot of earthquakes, so big seismic movements and seismic loads. So we have to design our facade to accommodate these movements, and this affects the joint dimension mainly. And the joint dimension will affect the thermal performance. So this just give you an idea of how holistically we need to approach facade design if we want to deliver a high performance system. And if we look at current policies between the US and UK, we see that in the US we are getting closer to targets typical from European and UK and was not like this. The picture is changing rapidly. If we look at the same code 10 years ago, we were far behind. So we're moving in the right direction, but there is still work to do. Especially one of the main difference that we noticed when we were discussing on this topic was that if you don't follow the prescriptive approach, but the performance approach, where basically allows the designers to trade all these values with a more efficient mechanical system. And this happen often because the performance approach is used 80% of the time in buildings designed in the major cities. So we have to do something to set a sort of backstop to guarantee a high performance envelope. And in the UK is slightly different, right, Carmelo?
Yeah, so the values shown here, like considered as minimum requirements for the fabric, are like backstop values. So it's not possible to do something worse or to apply something worse. But often, well, actually always, you need to do considerably better to meet the current requirements. And it's important to notice how in the UK that there has been a lot of effort on trying to minimize heating demand and so improving U values and air tightness. However, this is not enough and still far from net zero. And it's important to consider, though, that there are a lot of things changing recently also the new Bartel is going to come out here quite soon, and there is already guidance out there that exists that can help us in moving towards net zero. And I think we should say, well, towards a zero operational carbon-built environment. There is, of course, another part in all of this, which is the embodied carbon, which we're not going to mention today, otherwise we're going to keep you we'll keep you here for the next 2 hours. But for example, the guidance from LETI already allows to know what are the requirements for getting to what they call ultra low energy buildings for different typologies of buildings. So what are the EUI targets to have ultra low energy buildings? And the approach to go to a zero operational carbon built environment is to so have these ultra low energy buildings, which and then also increase the amount of electricity produced through renewables, so that we can get to a marrying point where the very little demand required by these ultra low energy buildings can be completely fulfilled by the renewable sources. And if we consider one of the most important categories of buildings, the residential buildings, we can see that according to LETI, there is quite a gap between what is defined as a ultra low energy building and where we are currently now, which is the gray bar. And I think what is important to notice in this is that if we look at all the areas which are considered to be key to improve, to get to the ultra low energy building condition, like most of these are related to the facade. So just to say that we believe that facade is key to achieve ultra low energy buildings. And I think it's pretty similar in the US, Andrea.
Yeah, exactly. You can see from this graph from the Department of Energy that both for residential and commercial, you have a big chunk of primary energy is related to the envelope performance, up to 50% for residential for both and commercial for heating, and cooling up to 60 and 70%. So it's really important that we design our envelope, both opaque and glazed portion, with high performance if we want to cut considerably the amount of primary energy and CO2 emission. And I think it's crucial to find the right balance between glass and opaque. And we saw in the past, I would say globally, in the past few years, that we're assisting a sort of fall of the glass box. So we are moving into the direction where we have a much more balanced ratio between opaque and glazing. And of course, that's not enough, but we will need also to push the performance of each component even further if we want to meet those targets. And if we look at typical build-up construction for residential and commercial, we can see that there are some differences between the US and UK. And for the next slides, we will focus on the California context, and just we want to highlight some differences. For example, on the screen now, we have a typical residential build-up in California, where you have a stud wall with 100 millimeters insulation, like mineral wall, and then a window usually with a small thermal break or plastic base. And the tension to the thermal bridge is not one of the major concern because of the mild climate in California, but this is not going to be enough anymore. We will have to pay attention to the thermal bridge if we want to meet the energy target reduction that it's going to come in place in California and other locations. Right, Carmelo, it's slightly different in the UK.
Yeah, it's quite different. So if we consider the traditional form of construction, so like what we're showing here on the screen on the left, you will notice quite thick layers of insulation between 140 and 200 millimeters. There is a lot of attention to detailing thermal bridges around windows. And if we consider like the type of glazing used, for commercial buildings is still mostly double glazed. For example, for residential buildings, we see that more and more like there is a switch to triple glazed units with either high performance or typically low coatings, depending on the GVALU requirements and requirements for overheating reduction. So and I think we also saw we're seeing in the UK that there is an increase in use of prefabricated and offsite forms of construction. Mainly due to the advantages that this can bring, like reduction in construction program, less prelling works, no issues with all the having to store materials on sites, but also especially increasing the quality of the works, and that can push. We said that preparedness has been key and has been always targeted in the UK recently, well, not just recently, but since a while. And if we consider prefabricated forms of construction, that can be, of course, further improved compared to a site-based approach. And if we look at the detailing of this in terms of construction, it's quite common to have to see large format precast or UHPC panels incorporating windows or doors. And I wonder, so is in the US also getting more frequent to use this kind of approach?
Yeah, definitely. We're seeing an increase in prefabrication of site for big residential development and an office building with unitized facade. And one thing that I just want to focus on is that, for example, in California, we prefer to do light precast if it's possible to reduce the impact on the structure because of the high seismic loads that we have here. And also, as you can see in the sketch here, we have much less insulation, and the tension to the thermal bridge. It's something that we have to work on even further. And if we look at typical unitized curtain wall that are mostly used in commercial building, we can see that, for example, in California, as I mentioned before, we have to really pay attention on the joints to accommodate seismic. So we end up with really big stack joints up to 25, 35 millimeter high. So this is going to affect the thermal performance. And another big difference with the UK, for example, it's that we have small thermal break or just a PVC thermal separator, and those are enough to meet condensation requirements or the current energy code here in California. But we have a lot of work to do to get to really low U values and meet future targets. And in the UK, it's slightly different.
Yeah. So there are quite a few differences. So if we just start from the stack joint, for example, we don't have to deal with big seismic loads. So it's mostly determined by structural movements, movements due to wind also, and it's usually in the range of 20 millimeters or less, depending on the size of the panel and the structural movements. And also, it's important to notice how we wouldn't really have any aluminum element like sticking out to keep to where you would fix the gaskets. Everything would be done behind the thermal line to avoid thermal bridging, which wouldn't allow us otherwise to meet the U value targets. And in terms of units itself, usually the approach is to have a speak-coated unit, and the glass would either be capped or structurally bonded. And I think there is quite another important difference with the US in general, not just California, is the glass buildup. In our case here in the UK, what we try to push to have both inner and outer pane laminated, but I think in the US you're not really using this approach yet.
Yeah, you're right. The baseline, it's monolithic inner and outer light. It's not going really to affect the thermal performance, but definitely having a laminated glass affects aesthetic and safety. So we're definitely pushing toward the European approach in our projects. And if we look at glazing and window framing, you can see a really interesting thing. If you remember, Carmelo mentioned that triple IGU were getting more and more popular, especially for residential application. Instead, in the US, if you see this graph from the Department of Energy, you can see that triple IGU, the line in green, we basically don't use triple IGU yet. So we definitely have to explore more and try to get to the same pace of the European Union. And if you look at the framing, you can see the massive difference in the dimension of thermal breaks between a typical aluminum window in UK or Europe and the one in California. And you would say, yeah, of course, but you don't really need that big thermal break because the climate in California is pretty mild. But if we transition to a higher performance framing, we can have benefit in summer too, because if you imagine that exposed frame exposed to high radiation and hot temperature, the heat flux will go from outside to inside and will affect cooling loads and comfort too. So if we transition to that bigger thermal break, we can improve substantially the surrogate coefficient of the overall window. and we can have much better performance. So we have goals and deadlines that are that we are closer than that we think, and like 230 California pledge for net zero energy, new commercial, or 2045 carbon neutrality goal, or 2050 for the UK and European Union and New York. However, we have other deadlines coming even sooner, like, for example, the 2022 all-electric new building in San Francisco and other cities here in California, that at first sight seems unrelated to facade design, but as California and other countries, and also UK is aiming to that, it's moving to an electric grid and turns to electricity for hot water, heat. The peak demand may start to move to the early morning in winter, and instead of summer afternoon. And a bad thermally performing envelope will exacerbate the problem of meeting the peak demand in early morning, for example, when we don't have much PV power, so it's not yet available because it's early in the morning. So for this reason, we need to push our envelope performance higher. How can we do that? Like, what are the strategies that we can implement to get to a higher building envelope performance? So of course, low values for both opaque and glazing, and combine them with external or dynamic shading to keep unwanted solar radiation out of our buildings, focus on reducing thermal bridges. Natural ventilation, of course, is crucial to reduce cooling loads, but also to guarantee healthy building and healthy condition for our users and occupants of our buildings. Reliable simulation to reduce the thermal, the performance gap that we currently see, and a strict collaboration with MEP is crucial to develop a system that works well together in terms of facade and mechanical. So let's see a couple of case study where we apply these strategies to move forward to net zero energy buildings. Back to you, Carmelo.
Yeah, so I think you mentioned like some keywords: reliable simulation, collaboration with MEP, and external shading. And we've seen that modeling complex external shading can be quite tricky, quite not straightforward. We came across quite a few buildings and projects where, in order to reduce the solar gain, use of external complex shading has been considered by the architect, by the clients. And I think in this instance, what is really important is to in order to reduce the performance gap, to make sure that we model these elements properly. So collaborating with MEP engineers is key, because we need to make sure that the parameters which are related to facade are accounted for correctly. So again, is key to have strong collaboration. And if we would consider the typical workflow for modeling external complex shading, so it doesn't seem like too difficult. You could there are tools like Ladybug, Honeybee for Grasshopper that would allow you to test different shading types and quite quickly in a parametric way. But the thing is, how do we communicate this information to the MEP engineer? So to check what are the performance of the shading, one could say, okay, let's assess the level of radiation on an elevation without the shading, and then include the shading, perform an annual simulation, and let's see how this performs. And we can get in this way a shading coefficient. That's true. However, you will have like dynamic conditions, which means the shading performance are going to change by the hour. And it's not possible really to pass this kind of information to the MEP engineer who's typically going to use IS as a software, because it's not possible to model hourly performance of the shading. What can be done is to input one single value. So even if we wanted to reduce the mass of data and say we're going to use like an average for a typical day of each month, for example, like in this table, which is showing you also how the shading coefficient changes between different times, different months. So that really creates a challenge. So what we did was we collaborated and did lots of work, with R&D work with Skelly and Kuch. And for this type of work, we also published a paper to understand what are the suitable methods of modeling complex shading in energy simulation. So what we did was to start from a baseline, from a simple shoebox model without any shading that we could make sure was giving very similar results in terms of energy consumption, both in Energy Plus, which is what we were using, and IS, which is what Skelly and Kuch was using. And then we decided to pick a type of shading, which you can see here on the screen, which was made of vertical and horizontal aluminum elements positioned in different way, like not in a let's say consistent, not in a consistent way. So we then explore what were the ways of implementing this external complex shading screen. First way that comes to your mind is, okay, we're not trying to just model it in your software. So either Ladybug, Honeybee with Energy Plus, or in IS. So yeah, it's possible to do that, and it's important to notice that immediately when we had to switch or to use it in IS, the geometry had to be simplified. So all the vertical elements of the shading had to be removed because of their size. That's already a level of simplification. This is what is method C1. Then there is a kind of traditional workflow approach, which I was describing before. We can let's say categorize or describe the performance of the shading with one single average value, either across the year or, for example, across a specific day, such as the design cooling day. So these were the two other ways of doing this. Then, and this was only possible to do in Energy Plus, it was possible to consider a BSDF function. So model the shading as a BSDF with a BSDF definition, then combine it with the properties of the glazing, and finally apply a window BSDF IDF property to the glazing in Energy Plus. And this was the fourth possibility, but only available in in Energy Plus, because IS doesn't allow to consider BSDF definition for energy simulation. And finally, the last method we tried that was also only available in Energy Plus was a little bit of a workaround. So surrounding our shoebox model with an enclosing box, which acts as a context shading, and it is possible to assign to context shading in Energy Plus hourly values of the performance of this shading. So actually, we could calculate, as shown in the first slide, all our shading coefficients hour by hour, and then provide a schedule to this external box. So yeah, doing it this way. And let's say this slide, which is summarizing the conclusion. So let's spend like just a couple of minutes on it. If we look at the graphic on the left side, this total solar energy transmittance, or GTOT, is showing how the performance of the shading combined with the glass are varying across the year. And we are displaying in the chart one average value per month for simplicity. So the blue line is our baseline, and is what is being calculated using radians. And then all the other lines you will notice are what we calculated using the other methods I just explained. And we can see that there is quite a lot of deviation. Like none of them is getting extremely close to the blue line. But for example, the brown, the orange, and the yellow, which are like C1, C4, and C5, get closer than the others. And if we then look at the energy use intensity, so cooling and heating loads, we can also make some more conclusions. So the C0, so the gray bars are our baseline, so it's the model without the shading. And we can of course see that there is a lot of cooling load and little heating, because it was highly glazed, and so lots of overheating happening. And then all the others are the methods. So if we start from the C1, which was modeling the geometry of the shading in the software, we can see that the C1, which is provides more reliable results, even if it comes with simplification. While the C1 of Energy Plus, we can see from the green lines in the chart on the left that is quite off from representing the real performance of the shading, especially in winter and especially in winter and in mid-season. The C2 and C3, which were related to applying a constant performance to the shading, calculated across the whole year or across the cooling design day, we wouldn't really recommend them, because it's not capturing the dynamic properties of the shading. So we just tested them to see how they were comparing with other methods, but we don't recommend them. The BSDF, we can see when we say here erroneous, is due to the fact that we are having higher heating loads with the shading than without the shading. So this method should be, in theory, very accurate to model external complex shading, but it seems that the way in which it's currently implemented in Energy Plus is not providing the results we would quite expect, which is why we define it as erroneous. And finally, the C5, which is the brown line here, is working quite well in terms of describing the performance of the external shading, but it can only be used in small models like Energy energy box, shoebox models. So there are different ways, there are different results depending on whether you use IS or Energy Plus. But I think the conclusion also from this study was that it's really key in this case is to collaborate with a mechanical engineer, because these external elements can be modeled and the results are not obvious. So we need to make sure that we are modeling properly and to minimize the performance gap. And I think I'll give it back to you, Andrea, going to the US again.
Yeah, thanks, Carmelo. In the second case study, we are going to talk about a specific kind of high-performance facade named closed-cavity facade, and if it's possible to use this kind of facade in a cooling-dominated climate like California. So closed-cavity facade is a specific kind of double-skin facade and have a non-ventilated seal cavity between the inner and outer glazing, and the exterior glazing allows to protect the dynamic shading within the cavity from wind and any dust or pollutant, because it's completely sealed. The internal glass, typically an IGU, provides thermal and solar performance in conjunction with the blinds. And in addition to prevent the formation of condensation in the cavity is constantly supplied with dry air or desiccant material that is integrated into the framing. So why we should use a closed cavity facade, right? This closed cavity facade has a low thermal transmittance with a system U value around 1.3 watt per meter square Kelvin, 0.23 BTU for the people from the US. So it has a positive impact on heating loads in the UK, whereas in California, we can take advantage of reducing the U value in order to get to lower cooling loads through conduction and increase thermal comfort near the facade in colder days. And of course, integrating automated Venetian blinds help reducing consistently gain through the facade, reacting right to the outdoor climate, and the extra glass of layer significantly improve acoustic performance of our facade. So the CCF have been implemented and have been proven their efficiency in terms of the thermal performance reliability in several projects in Northern Europe that are characterized by cold temperate climate. However, there are only few projects apply this facade system in a warm climate such as California, mainly due to concerns about cavity overheating and the effectiveness of the whole system in cooling dominated climates. So a client here in the Bay Area was interested in the system for a couple of projects. So we carried out a feasibility study to understand if such a system could work and which modifications are required to design and install it here in California. So we created this workflow. First, a simulation with the Energy Plus to preliminary assess the energy performance of the envelope system and hourly temperature across the year, and select key days during the year where we carry out finite element analysis to reassess the temperature profile in the system. And we perform our assessment, consider 3 different locations in California: San Francisco, Los Angeles, and Sacramento. These 3 cities have quite a different climate in terms of temperature profile. For example, San Francisco is being quite more temperate than LA and Sacramento. LA having average higher temperature across the whole year, and Sacramento is a bit more extreme with a rather low temperature in winter and really high peaks in summer. So we tested this shoebox model with different configuration of CCF, changing kind of coatings that we apply on the IGU, and single double coating solution, different materials for our blinds in terms of solar reflectance. And we compare the closed cavity facade model versus a typical DGU with a high performance coating on surface 2. And you can see here in the results the improvements in energy saving. It's pretty important, up to 50-60% for San Francisco and Los Angeles, instead a little bit less in Sacramento because of the climate condition where we have a lot of hot days and consecutive days, we have a consistent overheating of the cavity, so we have a little bit less advantage of using in Sacramento. And also you can see that just changing, for example, the color of the blinds or the coatings, we can get up to 5-10% combining coating and blinds color of energy savings, considering cooling and heating. And then we extrapolate, for example, the cavity temperature and the interior glass temperature for the different location and different configuration to highlight peaks and critical condition across the year. And for these days, we run really detailed finite element analysis to calculate the temperature in the cavity, temperature of the glass, and the framing. So we can see if we reach a critical temperature, and we can interface these values with a mechanical engineer to see if it's aligned with what they expect in terms of, for example, surface temperature for indoor comfort. So the client was happy about the results of this study. So we started working on a project here in the Bay Area, and in addition to our typical workflow and scope of work as detailing specification, we really work closely with the MEP engineers on this project, and we provided them data or story gate coefficient considering the different configuration of the blinds for the different angle of incidence on the sun, and really detailed glass interior surface temperature across several days, so they can use these data to build high definition CFD model that has been developed by Elemental in London. So they can assess air temperature and temperature distribution across the space and air speed, so we can guarantee high comfort for the occupants in the office building, and also trying to reduce cooling and heating loads. And at the end, thanks to this combined effort, we were able to remove most of the heating and cooling perimeter mechanical system, so with a massive positive impact in terms of energy consumption and cost, and still guarantee high comfort for the user. So with the two case studies that we just presented, we wanted to show sort of sneak peek on how our offices work together to develop high performance facades and collaborate with MEP to deliver fully integrated design that will help to move towards net zero energy building and hopefully meet the Paris Agreement. Thank you so much.
Wow. I don't know quite where to start with all of that. That was a fantastic presentation, really informative. I suppose if I can ask one question to start us off, when you said that sort of the facade is key for an ultra low energy building, do you think that clients really appreciate that? Do you think that sort of do they know that in terms of sort of, obviously facades as a discipline that generally gets pushed further down the line, I suppose, and so therefore do they generally appreciate that? And is there a difference between the two in terms of the UK and the US, between how the attitudes vary to facade design and what it can input into the energy usage of your building?
Who's going to start?
Go ahead, Carmelo.
Go ahead, yeah. I think we see more and more like an understanding about the importance of the envelope, which is also proved, I think, by the fact that we tend to be involved earlier in the design stages, also like on more frequently, or like also I think buildings which maybe a few years ago you wouldn't imagine to have like a facade engineer involved, like more traditional residential schemes, for example. So I think there is and it's also it's important to consider that the impact not only on the energy but also on the cost. So if the facade is not designed properly and we are not accounting for meeting all the right performance, it's going to be quite of a shock later in time when we get to procurement and to meet certain targets. just everything goes up in terms of also price and cost, because some certain things were not accounted at the right time in design. But yeah, certainly in terms of energy performance, and also like I will see more and more that clients are interested even in assessing, for example, embodied carbon of the facade, or life cycle assessments, or doing life cycle assessments in conjunction also with the primary structure. So we can see definitely a change, like in the attitude on this. I don't know if it is quite the same in the US, Andrea.
Yeah, I think that we were seeing the same trend in the past year, 2 years, maybe in the UK it was a little bit before us, but we are definitely seeing an interest from the client to pursue high performance facade. And I think one key element is try to explain them that if you have a high performance facade, you can save money on the mechanical system just from day zero, not just operational, but for example, in the case study, we were able to remove hundreds of meters of perimeter heating and cooling mechanical system. And of course, the facade was maybe a little bit more expensive, and if you can trade off the two, at the end, it wasn't that bad. So I think that it's crucial to really collaborate and explain, like, how can we find the money to use this solution.
Absolutely. I suppose it's sort of, do you have to submit to a building control in terms of sort of, structural engineers have to submit to a building control and have their calcs approved? Is that sort of a similar thing to in both countries for facades in terms of their performance against certain criteria?
I would say here in the US is less strict, right? For structure, it's mandatory, and here in the US, it depends on the state. Like, for example, Washington State and Seattle, they required certain certification for the facade. Instead, other states are a little bit less strict. So it really depends. But we always put in our performance specification targets to meet and calculation to be provided to support that the facade can meet those performance. Yeah,
performance targets.
Yeah, I mean, here is key, because you always need to coordinate with the mechanical engineer, ensuring that what we say the facade can achieve is also working for the whole building environmental model, and make sure we pass not only Part A, but other sets of not just regulations, but even, for example, there is in terms of overheating, there is guidance from CIPSI. So there are more and more requirements, and the facade has to cope with many more things than in the past, when not maybe as much considered. But yeah, regulations certainly not yet for embodied carbon though.
I wonder if that will help, kind of in terms of sort of, when it's mandatory for structural engineering, if it's a mandatory thing for facades, then actually that would really help in terms of the performance up to a minimum standard, or up to a particular standard for, say, embodied carbon or M&E integration for that, I suppose. It's really interesting, Andrea, when you're talking about the fact that there's a sort of you're resting on your laurels because it was kind of a mild climate, and so therefore you didn't pay much attention to, say, things like the thermal breaks within the facade. And actually that's kind of interesting, isn't it, that just because you have this mild climate means that you just don't kind of put the effort in to do that, but now actually there's a building movement to be able to kind of do that. And I suppose in terms of the triple glazing, I mean, Alessandro has asked, kind of triple glazing not even used in, is it used in Alaska or the colder climates and things like that, but is it just the fact that you can kind of, you've been able to get away with it in the past, and so now it's now you've got to start putting some attention into it?
Yeah, I think that one thing is that energy is pretty cheap in the US compared to Europe, so nobody really cares much. So also in really cold climate, we don't see that often triple glazing. I think that few examples, just for example in Chicago or Boston, but it's changing. I think that, for example, the Seattle building code with the new edition that is coming out pretty soon, if you want to, for example, build a facade with the window to wall ratio higher than 50%, with the target that they're forcing to meet, you have to use triple glazing, for example.
Well, that's good, yeah.
So I think that we are definitely moving in this direction, but I think that we will have a lot of work to do to convince the client that yes, something is changing. We have to move towards a high-performance facade, and we cannot rely anymore on the mild climate, for example, here in California, because if you overlook, we need to save every possible bit of energy and CO2 emissions. So we need to step.
Marginal gains almost. Yep. And in terms of the codes, what kind of, because I know that a lot of the stuff that you guys are doing are quite sort of, it's pushing the boundaries forward, but how does that work in terms of the codified approach? You mentioned the difference between performance and prescriptive approaches and things, but how are you actually kind of pushing that forward and trying to move it forward within the codes to make sure that all facades are pushed up to that same level?
Yeah, that's a good question. I think that we are trying to work closely with the legislator. For example, I'm part of the California Energy Code association, let's say. It's like a committee that is providing feedback to them, and we're trying to push them to, for example, introduce the backstop as in the UK, right? Just let's put a sort of limit to those numbers so we cannot trade off anymore. Working with this association, we're trying just to give feedback to the legislator that sometimes it's just using the market, what's available on the market, right? So sometimes it's just comparing to the small thermal break that is available, but there is much more. Like a lot of European manufacturers are now available in the US, so we can say, look, there are other manufacturers we can use and improve our performance. So I think it's crucial for us, especially in the US, to have a relation with the legislator to try to move forward.
And I suppose that's the real beauty of the fact that we've got kind of the offices in different multiple locations, and the fact that you guys work so closely together is the fact that, you can kind of share the knowledge between kind of what's best practice in both countries, and therefore what can work and in both locations, despite the fact that you've got this different climate and different kind of set of circumstances around, say, the seismic loading and therefore the joint differences and things like that. But so I suppose that's a real beauty in that. When you were talking about now, where have I written this down? Oh, the triple back to the triple windows, the triple IGU. Why do you think that is? Is it just that kind of is there no supply chain for it? Is it kind of sort of is it just not that it's been not done? Is it a cost thing? That kind of is that the same for both? Purely cost. Yep. They don't see the benefits of linking that together with the mechanical systems, and therefore the reduction in that kind of thing. Yeah.
I mean, here is also like it's not that common, but especially in residential buildings, it's getting more and more common to see TGUs, and the additional cost is not that much. But for example, for commercial, for example, there is not much of a need. I would say because there is also the concern about cooling if you insulate too much. But for residential, where you want to really, what was the diagram from Lady? Like you want to totally reduce as much as possible the heating, which you do it by improving air tightness and reducing the UL as much as possible. So of course, with a triple glaze system, you can get where no double glaze system can bring you. So.
Yeah, and of course, if you try to insulate more and more, of course, we need to take care also of the solar gain, right? Because if we insulate and then we trap the heat inside, it's going to be massive pain in summer. So when we think about improving U value, we have always to consider solar gain. So we need to keep it out as much as possible. Otherwise, it's not going to work.
There's always a trade-off to be thought about in terms of sort of between the different situations. In those kind of situations, I'll take a couple of questions from the actual questions section before I keep going on, because I could talk all the time. So Yuadui says, can a standard curtain wall be modified to use for a closed cavity facade, or do you need a custom system for the application?
Most of the time is a custom system. But the advantage of a closed cavity facade that it's much similar to a typical curtain wall than ventilated closed cavity facade. So the thickness, it's much similar to typical curtain wall. So I think that the closed cavity facade, it's moving in the direction, try to unitize as much as possible and bring it as close as possible to a unitized curtain wall. So that's advantage. There are a few manufacturing facade contractors that they have custom system, but now also off the shelf kind of system to try to use as much as possible this awesome system.
Does that also apply to retrofitting of buildings? Is that sort of, because we haven't touched upon, most of this is sort of the new buildings and things, but sort of obviously retrofit first movement in the UK, and sort of the huge building stock that we have in the office and the residential buildings and things. What can you apply for sort of the retrofit situation as opposed to new build?
Well, I think it's a broad question. Well, it depends. Depends on the existing condition. I think we recently actually worked on a DS competition in the US, where because in New York, so like in your territory, and for the 63 Madison Avenue, and we were proposing to refurbish the current existing curtain wall with a triple glazed performance aluminum curtain wall. So I think it depends on the if you need to preserve something or not. If you can rebuild the whole envelope, then you can go for the let's say most performing system. Eventually, even a CCF if it applies to the building. It depends really a lot on the building. If it is a quite regular building, then unitized system would be the best way to go. And also, for example, in that ADS competition, we also consider like what was the second scheme. So depending on the exposure of the building to radiation, we could apply different external solutions, which were an addition. So there was a first envelope, which was the base. It was quite efficient, and then in addition to that, how to adapt to the different climate conditions experienced by the facade on different elevations. But I don't know in your case, Andrea, if you have something to add on this, or
we usually just tear apart the entire building in the US. No, no, it's usually a refurbishment. Maybe you keep the structure, but then you refurbish the facade.
Yeah.
So you have a space to definitely improve the system. But if you cannot touch certain areas, you need to work on specific components like performance windows or stuff.
And I think there's going to be a lot of need for that. Like I think the local law 97 in New York City is asking that by 2030, all the buildings cut the emission of CO2 by roughly 50%. So if you don't, and most of that building stock is going to be existing still in 2050, but it's already quite old. So the way to do that is to refurbish. And so as Andrea was saying, if you keep the structure, you save a lot of embodied carbon, because the greatest part of the embodied carbon is really in the structure. And then you can even calculate potentially, if you put a new facade, you save in operational energy. How long does it take to you to offset the additional embodied carbon due to the new facade? But that you can offset with saving in operational energy and operational carbon.
Absolutely.
So yes, it's very important. We see more and more that we do need to refurbish.
Absolutely, and the retrofit stuff. And that was the competition you mentioned. That was with Wilkinson Air, the 63 Madison Avenue. Fantastic. It's a very exciting competition win that we had earlier on this year. Just to put that out there. So Casilla has said, what about user comfort differences? I have a feeling in the US it's not driving performance, yet in the EU it's more important. Examples are acoustic and thermal comfort, like triple glazing, to have less difference between surface and air temperature. Excuse me.
Do you want to go for it, Andrea? Or
I can go for it. I think that in the US, comfort is strictly related to the client, right? If the client really cares about who is going to be in the building and guarantee high comfort, we really have comfort as a high priority. Instead, if it's just not really interested and just more, it's in the second place in terms of concerns. So we really see that the client is really important if we want to push comfort. And one of the main reasons that we started looking at the CCF here was comfort near the facade. So try to maximize surface of the floor where you can have your employees working. So if you maximize, you can have more people in and near the facade, and we want to keep them comfortable too. So I think that that's the current situation right now.
One last question, I think. Or do you have anything to add? Sorry, Carmelo.
No. Just I was saying that also, for example, in the UK, I think something that's becoming relevant for related to comfort is the assessing the risk of overheating in residential buildings. Because like we were saying before with Andrea here, we've been pushing a lot on U value, air tightness, and then there is also more glazing normally than before. So our residential building can get quite warm, quite hot in mid-season and summer when there is sun striking on it, especially if you don't use external shading. So there has been, for example, in the last few years, guidance introduced by CIPSI to assess whether you are designing the building correctly to consider this risk of thermal discomfort for the user if they incur into overheating. So it's true. I mean, I think that is being really interesting point has been addressed here in that sense in the UK.
Well, that is exciting, isn't it? In terms of sort of moving it forward to a more of a person-centered approach, which is which, after all, is kind of the people who are going to control the building in the actual kind of, when it's in use. So there's one down here about. Sorry, I hadn't scrolled down. How is the modelling at hand correlated with the real-world performance testing? Do you get much feedback once the actual buildings are in use? Kind of, are you using that feedback, or can you gain feedback? Are clients open to it?
My answer on this is that I think we need to definitely have more of this, because I think currently we don't actually have much information on then how the building is performing when it's live, when it's in use. Well, there is the matter of the performance gap, which we discussed about, like you want to make sure that you model properly. But yeah, my experience that we don't have much information at the moment on this. I don't know. I think Andrea, you're saying yes, so I guess it's the same.
Yeah, we definitely need much monitoring of how the overall building and the envelope perform. So as much as we can do, I think it's better to try to bridge the performance gap and get better and better to predict how it's going to behave the system.
Yeah, I saw you nodding along there. Hopefully a quick answer to this one. Claudio, sorry. Any issue in terms of thermal shock for CCF?
No, we assess
quite specific on that one.
Yeah, we assess thermal shock on the glass, so we will select a proper temper state or heat treated state for the glass. It's usually the glass of the IGU facing the cavity that is the one more at risk. But it's not that critical because the entire system is cold or hot, so you don't have that big delta. But yeah, definitely we assess thermal break issue.
Yeah, it's more about your build-up. You want to make sure that your component, because the temperature may get quite high, like Andrea was showing before, but in a quite uniform way. So it's more making sure that your blinds, your motors, all the elements in there can resist to the maximum temperature you predict. So that we need to check that we don't go beyond certain levels. That's why checking that is very important when you design a CCF.
Yeah, material selection is crucial to guarantee the good
color
performance over time and durability.
Right, one last question. I know I said that about 3 questions ago, but this will be our last question because we're now pushing over the hour. But Megan has asked, other than the obvious moralistic value of saving energy in CO2 emissions, how would you go about convincing a client/owner to invest in energy-saving facades when it's the renter who will pay for the energy costs? Good question. One last question, basically. Are there any incentives for basically the client to invest?
I think that incentives and so the collaboration with the policymaker, it's something we definitely need to work on, right? Because if they can have some incentives to use this kind of high performance facade, would have benefit on their wallet, right, from day
absolutely.
0. So I think that it's crucial. I think that Australia did something similar a couple of years ago, tried to incentivize kind of high performance building, try to give some money back, or you can get more constructible areas. Yeah, exactly. Or you can build a little bit more, stuff like that. So I think that the sort of reward system could help.
But I think also, sorry, coming back to the New York City and local law 97, I think, but if you don't meet the requirements and the targets in terms of CO2 emissions, you're going to have to pay for your CO2 for what you emit in addition. So in that case, that's how you force the client to, because it's true, like he doesn't get any benefit from who is renting to pay a smaller bill or doing good to the environment, but he will have to pay for that if he doesn't do good to the environment. So, but that's how, I guess that's how you
give the environment a cost, basically. You give it a voice and a kind of.
Yeah, you have to offset your extra CO2 emissions by paying.
Yeah.
And that's on the developer. So.
Yeah, absolutely. And that ties in, I think, in a very broad way to what Max was saying last week in terms of in terms of the transition economy. But that's a much bigger picture. But as Max tuned in for last week, so have a look at that one if you want to tune out a bit more of that one. But I'll wrap things up now. But I would just like to say this is the last one in our series for the webinars. So thank you massively if you've joined us throughout the series, and thank you for joining us for this one. It's been really lovely to host this series and really educational. So I've learned a lot, and I'm very grateful for that. So if you would like to join us for the next series, if you'd like to get in touch, if you want to do anything in terms of collaborating, in terms of talking with us, then do get in touch. My name is Catherine Smale. I'm the marketing manager for Eckersley O'Callaghan. So get in touch if you would like to collaborate in any way, shape or form. We'd love that. If you would like to see any of the previous webinars that we've done, I think most of them have been recorded and they've been put onto our news site. So head over there. I put the address up on the top of the little chat function. So all that says thank you. Have a lovely Christmas if we don't hear from you before then. I hope that everybody stays well, and that next time we see you, the world will be a less topsy-turvy place. So much appreciated, everybody, and take care, and we'll see you in the new year. Thank you. Take care, everybody.
Bye.
Thank you all, guys.
Bye.
Bye. Bye.